Hi Steel friends. We're going to talk a little bit about two limit states. Those limit states for tension members are yielding and fracture. Now, you don't have to go very far to experience yielding and fracture. You can do this right in your own home. You have to look no farther than the trash bag. Right? So if you want to experience this video on your own, go ahead and grab a trash bag and some scissors, and you're going to have to make some cuts. So you just take the trash bag, I like to come down towards the end and just cut a strip, and you're going to cut a couple holes. Basically, you want to get something that looks like this. Alright, so this is what we're after. This is our basic tension member. As you can see, and I put a bolted connection on the on your left hand side there, so you can see two bolts on the hole. So go ahead and make this if you want to experience it. Otherwise, we're going to look at it on this demonstration. Now, as a tension member, if I was to pull this and basically try to rip it apart, what do you think is going to happen? You're probably thinking a couple things could happen, right? The whole member could maybe just stretch, or we're going to experience some sort of failure at this where we have these holes. Okay, and so if you answered one of those, you're on the right track. We're going to start with the first one. The first one is if this whole thing stretches, right? So if I go ahead and I pull on this, and I'll try to do my best here. If I pull on this, you'll see, you get something like this, and you can see the stretch as we go. If you remember back to mechanics and materials, right, we did a stretch strain curve for something like steel, and we saw that as we pulled on the steel, it would stretch and it would stretch and it would stretch. And you can kind of even see here we have some, you might be able to see the plastic kind of stretches. You get some 45-degree angle pieces, kind of like those Luder bands, where we're stretching and we're starting to experience, some sort of shear from, if you go back to Tresca's criterion. Basically, we pull on it and we pull on it and we pull on it, and now it's stretched, right? So this member is now permanently deformed and is longer than originally was. Yielding is a problem because it leads to what we call excessive deformations. And so excessive deformations in steel members is not good. You can see if this was supposed to be a certain length, now it's a couple inches longer than the original length. It's not a problem for this trash bag, but if that's your steel member and suddenly your steel member is 2 or 3 feet longer, right, depending upon how big the member is, 2 or 3 inches longer, would still be a problem. And so this is not good, and so we want to prevent this from happening in design. Now, when we look at limit state on yielding, right, the cross-sectional area has to be somewhere over here. This is the area that was resisting that pull, so it kind of be the end cross-section. So anyhow, when we go to look at the yielding limit state and come up with formulas, that's what we're going to have to use. If you want to, have another experience with yielding, one of the things I used to do when I was a kid, I was one of those kids that after I finished my, juice box, I would grab the straw and I would pull on it. So you can go ahead and give that a try to get the straw to yield. So you get something like that. You can see in there you have kind of the yielding, the reduced cross section. It's fun if you do it and you do it really quickly. You can even grab the yielded section and you can feel that the yielding dissipates heat as one of its energy losses. But you can see that now the straw is permanently deformed. Now if I go to use this straw like normal, it would kind of work, but not real well. You'd probably be annoyed, so I always did this to my juice box straws after I finished drinking, of course. But anyhow, so those are a couple ways you can experience yielding right in your own home. Go ahead and give it a try. We're going to develop a formula for yielding. Our first tension member limit state then is yielding. We said that yielding was a problem in the gross cross-section of the member. And we defined the gross cross-section as the main portion of the member that's resisting the tensile force. We call the gross section AG in steel design.
The problem with yielding, as we showed in the demonstration, was that it leads to very excessive deformations. And that is why we don't allow tension members to exceed their yield capacity.
Now we're going to look at fracture. A lot of you probably saw this thing and said immediately it was going to fail over here at the connection, right? And you probably think this because look, right at the bolted connection, right, we have less material resisting the force, right? And so when we pull on it, we're expecting failure to occur probably at this cross section. As I do this, you see that I pull, you see we get yielding, and then very quickly we end up getting fracture. One of the things about fracture is you have to use what we call the net section. So when we come up with our formulas for fracture, we're concerned about fracture because it causes physical separation of the member, and that's pretty dangerous, especially as we're designing like a building or something like that. That's pretty bad. So we want to prevent physical separation or permanent separation of our connections. And so that's why we check for fracture, and you want to make sure you use the net section area. And so that's the area here.
And let's take a look at fracture. So as we saw for the demonstration, we're worried about fracture at what we call the net section. And in a particular connection, we're concerned with fracture at what we call the leading edge of the connection, or the forward edge, the first line of bolts. And that is where we take the net section area, which we'll define as A sub n. And then as you saw in the demo, the biggest problem with fracture is that fracture leads to permanent separation of the element. And so we cannot have that in design. We need to make sure that all of our members are staying together. So that is why we hold fracture as one of our critical limit states.
The most common question I get about this demonstration is that why do we not check yield at the net section? All right, and so I just want you to think about this for a second. It's not that the fact that at the net section we don't experience yielding. If you go back to that video and you look at it, you'll see that as I pulled, we first got stretch at that net section, and then we got fracture. And so we have to remember back to kind of our stress-strain curve diagram. We're always going to experience yielding before fracture. However, when we look at it just in terms of the overall length of the member, when I experienced yielding at the connection, I only stretched a very small amount. Okay, and so we have a very limited amount of stretch right at the connection. And so we're not really concerned about that. If our connection stretches just a little bit, the member is still largely useful and we're okay. The only problem we run into is if the connection stretches and then it eventually reaches its ultimate capacity and then the connection fractures and separates. That's when we have the big problem. We're concerned about yielding now in the gross section because over the entire member, if the entire member is stretching, that's a lot of, that's a strain, the yield strain, but it's multiplied by the entire length of the member. And so now, instead of picking up maybe only, where at the connection we're picking up, 0.02 inches or something of deflection, over the entire member, now we're picking up 3, 4, 5, 10 inches deflection, whatever it happens to be. But we're picking up a lot, and then that's just not, we can't use that member anymore in design when it changes geometry by that much. So that's why we check yielding for the gross section, but then we only look at fracture at the net section.
All right, to help you better understand this, let's take a look at the steel stress-strain curve. And I want to do this for two different points, one point in the gross cross-sectional area and one point in the net cross-section area. Now we want to consider different time increments, right? So say we apply a load at some time, which I'll call t equals 1, this would be the state of stress at the net section, while this would be the state of stress at the gross section. The state of stress at the gross section is lower than the net section because there has more area. We keep applying load, so eventually the net section reaches yield first at time instance 2. But the yield that the gross section is still in the linear elastic range. We keep doing this, so now the net section is going up the strain hardening region, but the gross cross-sectional area is still in the linear elastic range at time instance 3. At t equals 4, the net section has now reached its ultimate stress, and at t equals 4, we still see that we're in the linear elastic range for the gross section. What this would cause immediate failure, right? Because now the net section will have exceeded F sub u, and this will lead to fracture. So in this particular instance, this member would be controlled by fracture because the fracture limit state would be more critical. Now we're going to undo this, and we're going to take a look at a case where yielding would control. So say for a particular member in geometry that when we look at this at t equals 1, here's our state of stress in both the net section and then at the gross cross section. But now they're a little bit closer together because maybe the hole diameter is a little bit smaller, maybe the width of the member is a little bit bigger. As we keep doing this kind of game, the net section is still ahead of the gross cross-sectional area. It's just that before the net section can reach the ultimate capacity, the gross cross-section hits the yield. And then this would lead to yielding across our entire member. And then that would end up with large excessive deformations. And so this is a case where yielding controls.